to the next research talk by Max.
Thank you.
Lübbering. Thanks, Anna. Max, are you here? Yeah.
Yes, I'm here. Can you hear me?
Yes.
Perfect.
Very well.
Then I will share my screen.
Please go ahead.
Can you see my screen?
Yes. So Max is going to talk about Datastack, unification of heterogeneous machine learning dataset interfaces. Go ahead, Max.
Yeah, thanks a lot. So yeah, my name is Max Lübbering. I'm a PhD candidate at Fraunhofer IARS. And together with my colleagues Maren Pilka, Ilham Schengeseng, and Rafet Zifa, we proposed Datastack, which is an open source contribution towards unifying heterogeneous machine learning dataset interfaces. So normally when we start a machine learning project, we start with looking for a dataset in one of the famous dataset repositories. That could be, for instance, UCI machine learning repository, Kaggle datasets, or for instance, Microsoft Research Open Data. And on these repositories, the datasets, they come in lots of different diverse raw formats. So there's, for instance, raw text. There can be tabular formats such as NumPy, CSV, or pandas data frames. And sometimes you also have even medical formats, for instance, DICOM for MRI scans, for instance. And when we want to integrate such a data set into our machine learning pipeline, there are usually three recurring integration steps, namely the first one being the retrieval of the data set from the hosting repository. And then in the second step, we need to preprocess the data, we need to clean it such that it is in the shape for our to work with our machine learning pipeline. And then in the third step, we implement the custom iterator that iterates through our data. Okay, so this can actually result in a couple of issues. So if you think about it, like you have a set of different data sets and you want to integrate all of them, this can easily, for instance, lead to code duplication because you just copy and paste the code. Basically, often there can be also hard-coded paths, etc. And this can be very susceptible to bugs. And yeah, having to implement all these three integration steps over and over again, it's also time-consuming. And yeah, this goes, and the third point goes a little bit into the direction of the first one, actually. It can easily lead to a flawed architectural design from the beginning of the machine learning project. There are some existing open source projects which integrate already all these three integration steps already, and it's very convenient for prototyping and benchmarking your machine learning algorithms. And the way they do this, they basically provide you with an iterator, and internally then do all these steps of integration, retrieval, preprocessing, and also iteration. There are also some downsides towards this. So mostly they use custom data structures. So for instance, TensorFlow data sets and Hugging Face data sets, they use TensorFlow tensors, and Torch Vision uses Torch tensors. And by this design, there's not an immediate cross-framework support. It can be also quite difficult to extend these because often, like the way they are implemented is that you have an iterator, and they all do the things of integration, namely retrieval, and as well as preprocessing, like in a single file. And for a new machine learning engineer, it can be quite difficult to just extend these kind of data sets. So we took those things into account when we wanted to design Datastack, and we defined three requirements for our framework. Namely, we want to have a clear separation of the components, namely retrieval, preprocessing, and the iterator, such that we have a clean separation of concerns here. And we also want to support arbitrary data formats. So we don't want to be limited, for instance, to pandas data frames or NumPy arrays. We just by design want to support any data format. And we would also like to be machine learning framework agnostic. So by design, any machine learning framework should be able to be supported. And to achieve these goals, we made two proposals, namely on the interface level, we want to only handle the data formats as raw byte streams. So for instance, when the retriever has to communicate with the preprocessor, we always communicate as, or just we pass just byte streams as data. And internally, those components, they then have to like cast these byte streams to the specific formats. So for instance, if the preprocessor receives a byte stream from the retriever, it has, for instance, to cast the data to a NumPy array internally to perform the preprocessing. But the main part is that on an interface level, we always have byte streams. Okay, so this is how we worked out our architecture. And here I showed like the implementation for a single data set. Namely, we have a dataset factory, which calls the retriever in case the dataset is not present on the local disk yet. And the retriever then downloads the dataset, so the raw dataset from the cloud repository, and stores it on disk via storage connector. And here already we just work with byte streams. So the downloaded raw dataset the download contains only byte stream, and also when we store it, we just store it as a byte stream. And then in the second step, the preprocessor loads this raw dataset again as a byte stream, and then internally casts it to the specific file format that is needed, and then subsequently performs the data cleaning on it. And then afterwards, the cleaned dataset, so the preprocessed one, is again being stored on disk by the storage connector, again, just as a byte stream. And then finally, the iterator loads this preprocessed dataset, again, as a byte stream, and it casts it to the specific format that is needed for iteration. So as you can see, basically that on all those interfaces, we always use just byte streams, while internally we can do whatever we want to do with this byte stream. Like we can cast it to our files or like to our specific formats that is actually needed. It also has another advantage, the way this is set up, because we can support by design already lazy loading. So let's say we have an H5Py file, which is stored on disk. And now the iterator can just lazily load the data that is needed without having to load the entire byte stream into memory. So besides what I just said, like we also have higher level iterator functionality. And this means that we can arrange our iterators in a way that we solve more complex iteration functionality. And here I show 3 of such operations, namely stacking, splitting, and joining. So for stacking, we start with a base iterator, which is loading the data from disk. And then we can have on top different types of iterators that just work using the child, basically, the child iterator. And in this particular case here, we are using an iterator view, which just considers a subset of the indices. And so by design, we can already like filter certain samples only and don't have to iterate through all the samples that are within the base iterator. And then, for instance, we can have another iterator which loads everything into memory to make the iteration way faster. And then there can be also custom iterators that can be implemented by the user of our framework. We also have some splitting functionality, which means that we again start with a base iterator. And then we have 2 iterators, which only consider a subset of the indices from the base iterator. And if the subsets are disjoint, we basically have a split, or like we have actually 2 splits in this case. And yeah, I mean, obviously this is very convenient when you want to do machine learning, because you always work with a train, while, and test split. And you can use this function here to work this out, basically. And then finally, we have the joining operation, which means that we have, in this case, multiple base iterators, in this case, iterator A and iterator B, and they can be merged into a single combined iterator. This comes in very handy when you have like a train while test split, for instance, which does not really reflect your use case. And for instance, you want to have different splits. In this case, you merge them into this combined iterator, and then you could work with a splitting on top of this combined iterator to get your custom split. Okay, so while this, so in the previous slide, I just showed it like theoretically what we can do. And in this slide here, we see a practical use case in which we actually used Datastack. And it is a dataset preprocessing pipeline for evaluating the robustness of a machine learning model. Again, we have our base iterators. So in this case, it's an ATIS, Reuters, and NewScripts iterator, which are all based on text data sets. So in the first step, the ATIS iterator is being split into train, val, and test, and then subsequently being loaded into memory to make this way faster for iteration. And then, all right, let me actually talk about a little bit more about this here. So this is kind of the classification setup that we normally have, right? So we train, validate, and test on the same classes that we trained on, basically. And now if we want to evaluate our model robustness, we check how our model reacts to samples that come from classes that we haven't trained on. And this is what we use our other iterators for. So these are the ones that we haven't trained on. And we filter a couple of classes here. So we apply label filtering. We receive a new iterator, namely outlier iterator 1 and outlier iterator 2 for these two iterators here. And then we join them with a subset of the classes from test 1. So we also applied label filtering here. And then we come up with two new joint iterators, namely test 2 iterator and test 3 iterator, that are then finally loaded into memory as well. And this is how we can then actually evaluate our model robustness, because we can see, for instance, how certain our model is on outliers. And normally what we expect from a model to predict is actually that is highly uncertain on those outlier samples. And this is what we can measure here. So yeah, what can we conclude from this? We propose Datastack, which is a generic open source framework for machine learning dataset integration. Its main advantage is that it's completely file format agnostic, because we only handle all the data formats as byte streams on an interface level. We also showed that we can like reuse iterators. We can arrange them in a hierarchy to solve higher level functionality within our machine learning pipeline. And then for future work, we would like to implement further higher level iterators to make it even more convenient to use Datastack. And we would also like to support enterprise level storage solutions. So right now, when I was talking about the storage connector, it is just basically storing the information as a key value pair on disk. So nothing fancy here. And for the future, we would like to support enterprise level storage solutions. And then finally, we would also like to integrate Datastack into ModelGym, which is another open source contribution from us, which focuses on reproducible machine learning research. And the why we actually want to do this is because if you think about this entire hierarchy of iterators, it kind of resembles a huge part of the machine learning pipeline. And if you specify this hierarchy, for instance, in a config file, a new researcher could just browse through the config file and see how the project was set up. And it's way easier to reproduce machine learning research due to that. So yeah, if you're interested, feel free to check out Datastack and ModelGym. If you have any questions, yeah, just drop me a line. I'm happily answering any emails. And yeah, thanks a lot.
Thanks, Max, for the presentation. We actually have some time for question and answers. Yeah? So are there any questions from the audience? Rehan, you want to say something? Or
actually, I want to have a clarification question. So when you say dataset integration, what is the definition of it? You are not trying to integrate schema or data, but to make sure all the data sets have the homogeneous format. Am I correct?
Yeah, I think Yeah, partially I think it's correct. Like we want to integrate or like we want to pre-process these data sets into a specific format. And this can be done using custom implementation, which Datastack does not really know about. And it's like up to the user who wants to integrate this data set basically, and we just provide the framework for it. And on an interface level, we achieve this just by using these byte streams on an interface level. Does this answer your question?
Yes. So, and also I'm a little bit interested, since you say you are data streams, how is the scalability of your approach? So when I have a large scale and high speed data streams.
Let me think about it. So the way we're handling it is like in Python, you have file-like objects, and they are basically the same as a byte stream. It's the like the equivalent, and we can parse as fast as the system allows to basically parse a byte stream. So I think this is the bottleneck that we have, and then internally we could scale it up based on the pre-processing implementation. Like if we use multiprocessing or other or even other frameworks for stream to work with streams. I think this is like where we could work or like improve the scalability. But I think the bottleneck that we actually have is basically how fast can we read this byte stream.
Thank you.
Thanks. We have a question from Paul. Paul, please unmute yourself and speak. Just speak. Oh, I think we need to unmute Paul.
There we go. Sorry about that. So do you wrap any of these existing dataset interfaces? Like, I mean, I guess it would be really nice to already support something like Hugging Face or any of these to kind of have a facade over that. I was just kind of browsing through your repo and I couldn't figure it out, but
yeah, we don't have it yet.
I see. Okay.
Yeah, but yeah, definitely that's a really good idea, because we would immediately support lots of data sets actually. And yeah, we have one small repository where we are using our own research data sets in, and that worked quite well so far with us. But if we want to scale it up and make it easier for other people to also use it, this is a really good idea.
Then thank you, Paul and Max, for the presentation.
Thanks for having me.